Now for homework 1, part 2, we're going to, assuming that a decrease in air temperature, so, walking out of a mountain, you get less air pressure and a little colder, right? Excuse me. Can be entirely modeled by an adiabatic reversible expansion of pockets of air, and it's an ideal gas. So starting from the basic equation of fluid statics, derive expressions for air pressure and temperature as a function of altitude. Okay, so let's move over to the iPad. So how about our basic equation of fluid statics? We can model that by saying that a small change in pressure over a small change in altitude, z, we'll call that z for this video, can be modeled by negative gravitational force constant. Actually, I would rather put density first. Okay, density times gravitational force constant. And you might wonder to yourself, why did you put a negative there? That doesn't seem immediately obvious. If it were me, I would not worry about it. Forget about the negative and just put in density times g, right? Now, the reason why it's negative is you might land yourself in a tough spot if it weren't there. And we'll see that later. I'm not going to model why, but you will land in a tough spot. Trust me. The reason why it's a negative is we're modeling this with altitude, right? Where we say that z1 is lower than z2. Going upwards means positive, right? I don't know why I drew a dipole arrow. It should just be a normal arrow. Going upwards is positive, right? Well, if we have force of gravity, the force of gravity is downwards, so it would make sense for this to be negative, right? And that is why. So let's see if we can move some things around this equation, expand it out a bit to make this equation make sense in the context of an ideal gas. So if you look at density is unit mass per volume, right? If you look at volume for an ideal gas, you can relate volume to every other variable of a ideal gas by using the ideal gas law. So we can say that density is equal to mass times pressure over nRT. Heard that before, right? What else have you heard before? You've heard that mass kilograms over mole is what? Molar mass. So molar mass times pressure over RT. So now we can rewrite our basic equation of statics like so. By the way, the direction we're heading is we're going to massage this equation further and further and eventually solve it. We're going to solve it as a separable differential equation with dummy variables of integration with assume known values of pressure and temperature. Okay, that's the road we're headed down. Okay, so that you will start this video and wonder what the heck is going on. So dP/dC is equal to molar mass times pressure over RT. Okay, so now what do we have? We have a differential equation. This is our basic equation of fluid statics, but we're left with a independent variable t here that will get in the way of our solvability for the differential equation. So how do we deal with that? We'll deal with that by relating it to pressure using the second law of thermodynamics, which states that for a small change in internal energy, that is equal to the change in enthalpy minus external pressure plus a small change in volume. And we have some considerations that makes this equation a little bit nicer to work with. We're told that it's a adiabatic process, so we now know that there is no change in enthalpy. Because it's an adiabatic process, the change in internal energy can be modeled by a small change, a differential change in volume per change in temperature, held at constant volume. Okay, and we know this multiplied by differential change in temperature, and we know this to be our heat capacity at constant volume dt. Okay, and one more, we know that since it's a reversible process, the external, let me double check that my audio is recording properly. Yes, it is. We know that since it's reversible, the internal pressure must equal the external pressure. So PEXT is actually in reality just plain old P dV. Okay? Now, we still have P here. We need to change it to the other variables of a ideal gas, and we do that by ideal gas law. And for ideal gas law, for specific volume, that's what these terms V is in for the second law of thermodynamics. P is equal to RT over V. Okay, so now what do we have? We have CV dt is equal to RT over V dV. We have a separable differential equation. We gather up our independent variables. So CV 1 over T dV, or dt rather, dt is equal to R 1 over V dV. Now this raises the question, well, what are our bounds of integration? Well, again, you'll know that these now become dummy variables of integration, because in order for this to work, we find that we must know the temperature and volume of an initial point, and we're exploring the altitude and seeing what is the temperature and volume of another point relative to the initial point. So we say that, well, we actually know a temperature T, and we're looking at a new temperature T. And again, same thing for volume. We know a volume, but we don't know what the other volume is. Okay? So then we go on and integrate this, and we get CV, let's see, natural log of T over T1. So R natural log of V1 over V. Gather up your constants, CV over R, and natural log T over T1, natural log V1 over V. You'll find that with log rules, we can throw that inside the log, and now that the logs are the same, you can just cancel it out. So you're left with T over T1 raised to the heat capacity at constant volume divided by the universal gas constant is equal to a known volume V divided by an independent variable V, volume. Again, remember this is specific volume, not plain Jane volume. Okay? So, to remind you of what the roadmap is looking like, we're trying to isolate T so that we can plug in an expression for our main equation. Okay, and we're going to do that by first, well, what else do you notice? You notice that we're left with volume here, which, again, isn't necessarily in our differential equation. So we'll actually want to change this and apply ideal gas law again, and change this to our other variables of a gas, ideal gas. So we actually say that V1, the known volume, is equal to R times a known temperature times a known pressure over R times a independent variable temperature times independent variable pressure. So what do we find? Well, we find that R cancels out. We do some fraction work. We see that it's T1 over T multiplied by a known pressure. Actually, rather, I need to be careful with fractions here. It should be P over P1. Okay? So we have this. What do you notice? Well, you notice that this is the reciprocal of that. So if you multiply or divide, otherwise multiply the reciprocal over this, there's two of the same base. So, T over T1 times that. So we actually get an exponent of plus 1. Okay? So let's go ahead and do that. So temperature over a known temperature is now equal to CV over R plus 1. equal to pressure over P1. We'll call on one more relationship, and that relationship is that, well, we know that C, the heat capacity at constant pressure, is equal to heat capacity at constant volume plus R. This is a known relationship. This we can use to apply and simplify here by like so. We can factor out a 1 over R, so we're left with a CV plus R 1 over R. We see that CV plus R there, right? So we actually have heat capacity at constant pressure over R. So let's move on. We now have temperature over known temperature raised to the power of heat capacity at constant pressure over R is equal to pressure over known pressure. Well, the end is in sight, right? You can see how we can clearly algebraically solve for T now. So why don't we go ahead and do that? Let's go ahead and do that. We now have T over T1 is equal to pressure over a known pressure raised to the power of R over heat capacity at constant temperature, and multiply the known temperature over. So the independent variable temperature is equal to independent variable pressure over a known pressure multiplied by a known temperature raised to the power of R over Cp. So here's another useful relationship that we've just derived, and we'll plug it into our differential equation above. But here's another useful relationship, and you'll notice that well, we no longer have a not so convenient independent variable in our differential equation. We do have some known values that we need to know now, but we also have this pressure here that we can throw in and solve our differential equation. Okay? So you'll notice that I've taken the liberty to move us to a new page since we ran out of room in the last page and copied over our relevant equations. You'll also notice that I noticed a copying error. There really should be a G there, gravitational force constant, right? So let's go ahead and plug our T in there. We're going to have negative molar mass Gp divided by R, known temperature times P raised to the power of R is Cp over P1 R over Cp. Okay? So, what are we going to have? This is going to equal negative molar mass G times pressure times known pressure R over Cp over R T1 pressure times R over Cp. And again, this is set equal to our derivative. So it's a separable differential equation. And we will solve it like so. So on the left hand side we'll have pressure. We gather up our pressure terms, and what you'll notice about it is that it's PR over Cp, R over Cp divided by P. That in reality means that it's raised to the power of -1 dp. And you'll notice on the right hand side, all we have, let's see if I can plug my iPad in. It's running really low. Let's try that. Some room. Keep this propped up. There we go. Let's try that. You'll notice on the right hand side, all we have are constants. So negative molar mass G, known pressure R over Cp over R T1. That's it. dz. Integrate, and as always, we'll ask ourselves what should be our variables of bounds of integration. Well, we will know information about one point, and we're exploring a point relative to that, and this becomes dummy variables of integration. Then we integrate. Over here it's easy and convenient because of that -1. We get R over Cp, P raised to the power of, actually, should be reciprocal. there. CP. This is yeah, I think I can do that. Minus P1 R over CP. Yep. I need to be careful there. Equals negative mg P1 R over CP over RT1. In this case, change in altitude, C minus C1. Okay. You will notice that that cancels out, and we can bring CP to the other side. So we have P minus P1 R over CP equals negative molar mass G P1 R over CP over CP over known temperature times change in altitude. Okay. We can bring this over to the other side by adding. So we have P R over CP equals P1 R over CP minus molar mass times G times P1 R over CP over CP T1 change in altitude. And you'll notice that we have like terms here. So we can factor that out. And we have P over CP equals P1 R over CP 1 minus molar mass G over heat capacity at constant pressure times known temperature times change in altitude. We can take the reciprocal, power of the reciprocal to both sides. So we're left with P1 times the quantity 1 minus molar mass times gravitational field constant over heat capacity at constant pressure times known temperature times the change in altitude. And there we have it. We now have an expression for pressure as a function of altitude, assuming a adiabatic and reversible process. Okay, so let's move on. The next part is not much, I promise. Not much. And let's see, we'll copy this. Copy the equation that we just derived because we'll use it. Okay, we now want to find an expression for temperature. Well, that is easy peasy. Because guess what? We have an expression which relates temperature and pressure. Right? Check that out. It's not quite usable yet. We just have to massage it a little to make it usable. And we do that by isolating pressure, because we want to be able to plug that in there in terms of T, right? Two simultaneous equations. So now we have T, temperature over known temperature, is equal to P over known pressure raised to the power of R over Cp. So T, temperature over known temperature raised to the power of Cp over R, is now equal. Oh, did I do a copying error? Yeah, I did do a copying error. Cp over R. Cp over R. Yeah, there we go. Cp over R. Okay. Is equal to times P1 is equal to pressure. Oops, not R. Pressure. Nope, I did R again. Pressure. There we go. So we plug that in for pressure. Right? So let's try it. We have P1 T over T1 Cp over R is equal to P1 1 minus molar mass times gravitational field constant over heat capacity at constant pressure over known temperature times the change in altitude. It's equal like that. Oh well, guess what? Things cancel out rather nicely. rather nicely. That goes away, that goes away, that goes away, that goes away. We have T equals equal to T1, 1 minus, that should be molar mass, not just mass. Cp T1 times the change in altitude. There you have it. We have a easy peasy expression for temperature as a function of altitude. And this concludes part 2 of homework 1.